Okay. Good morning, everyone. My name is Mojgan Farahani, and I'm starting us off this morning on behalf of the CINET Junior Scientist Council. Our speaker in this seminar this morning is Dr. Andrew Margenot. And I just want to note that this seminar will be recorded. And he completed his PhD in soil and biochemistry at UC Davis on soil organic matter and phosphorus cycling in tropical agroecosystems. He joined the Department of Crop Science in 2017, where his research group studies the biochemical basis of soil function from molecular to landscape scales. And his key research area is the Goldilocks nutrient of phosphorus in agriculturally dominated landscape of the US Midwest. And he's going to talk to us today about legacy phosphorus and opportunity and need for linking soil water research. So without further ado, let's welcome Dr. Margaret. And you want to take it away?
Sounds good. Thank you, Mozgan. Well, so first I want to thank Dr. Kumar for having me here, and Dr. Rhodes as well. I met with them for the first time a few months ago in August, and they were quite kind, and they invited me to give what is more of an introduction to the group of what some of the things of what my lab does and ways that I think that our lab could collaborate and support the work of CINET. So I'm happy to be here. Thank you for having me. Okay, so what the topic is for today, I understand that I've got about 30 minutes to pitch something and then for us to have a healthy discussion. What I'd like to do is to make the case that soil science has been siloed and not really talking to hydrology and geology when it comes to the transfer of phosphorus from soils into waters. And to build to that, I want to provide some background on the soils end of things when it comes to phosphorus, specifically phosphorus that accumulates over time, known as legacy phosphorus, and what the implications are for water quality. As you'll see, there's a different take on phosphorus and how we study it in the skin of the earth, as a geologist might call it, the soil. But there's, I think, a lot of shared, that there's a need for a shared approach that integrates hydrology with soil science. So that's my goal for today. The Goldilocks nutrients is how I think of phosphorus from a agronomic or agricultural perspective. I'm not an agronomist, I'm a soil scientist, but I work with agronomists because we humans have pretty much used most of the ice-free land area for crop production. So it's hard not to talk about agricultural use of soils when doing soil science. So the term Goldilocks simply refers to the little too much or a little, either too much or too little. So for those that may not know the Goldilocks story, it's the story of a little girl goes into a house and there's bears. Don't ask, it's a weird story. Basically, this little girl is trying to eat soup, and one bowl of soup is too hot, one bowl of soup is too cold, and the middle one is just right. So phosphorus to me stands out as a Goldilocks nutrient. In much of the tropics, it's severely deficient because of high weathering of soils and then inability to access fertilizers. And in the developed world that's highly industrialized in agriculture, we have a little bit too much of phosphorus to the point that it's now leaving soils and entering into surface waters. And there's very few places that get it just right in terms of balancing the agricultural needs with the environmental demands of agroecosystems. So with that said, let me just launch into this. First, I want to thank the funders who have made this possible. What you're about to hear is one of the main thrusts of our phosphorus program in my group. And we have a whole lot of different sources of funding going from NSF to commodity boards like the soybean board. But the theme through all these different projects is trying to take a biogeochemical soil perspective to phosphorus that can improve on the to date largely agronomic approach. And of course, this is people who make it happen. So thanks to these 5 individuals in particular, they're on the phosphorus theme research lines, and more specifically, they're all working on Legacy P in some way. So Dr. Zhou is a alum from this very program, from the CINET. So we are fortunate to have her in our lab working and leading the effort that you're about to hear about. And finally, as you'll see, I have some open positions. So a shameless plug is that if you're looking for a postdoc on this topic, we do have 2 funded positions, and you could be part of the team. All right, so a bit of an overview of what I want to talk about. So to lay down a pretty blatant, clear definition or goal, excuse me, the pitch here is that legacy phosphorus, which can be defined from a soils or a water perspective, but in either case, there are linkages on legacy phosphorus between soils and waters. And so to really solve this challenge to water quality, there needs to be a better integration of soil science with hydrology, or at least that's what we think. And what I want to talk about are really 3 points that set up for, or that are in support of this. The first is that you might think of these as questions rather. The first is, why do we care about legacy phosphorus in soils? And I'm saying in soils because there's also a water-based definition of legacy P. So for legacy P in soils, why do we care? Second is, well, how do we define, and as importantly perhaps, how do we measure legacy phosphorus? This is trickier than what you might imagine. The theme will be balances as an indirect way of, by difference, estimating how much phosphorus has accumulated in soils, but difference approaches aren't so accurate, especially at the finer spatiotemporal scales. So let's say sub-watershed and sub-year, for which a lot of the losses might be happening. And the third question that I want us to think about is, at the end of this, how does water and geology, the critical interface, why does this matter for soil legacy phosphorus? And I see this as being one of the main points of our discussion in this in the final third of today. So as a reminder, we are situated up here, a great figure from a really nice paper that I like to use to position where we are as soil scientists. Again, we're the skin of the earth, as the geologists say. We're looking at the top 1 meter or so. What is soil and how it changes into something else is somewhat philosophical. Even what soil is, the definition recently changed according to the Soil Science Society of America. But I think it's, when you see it, you kind of know. We know that the very, very top, what is the black stuff in our region of Illinois, that's easily discernible as soil. And as you go deeper in our landscapes here, we have loess, typically over some kind of a till. That's the transitional zone. So for today, we're really talking about the top meter, the solum. So the solum is everything but the sea horizon. So we don't have many O horizons out here, but largely the A, the E, the B horizon. So what's going on in the solum? The solum is what you might think of as what humans are enriching with nutrients to support crop production. And they do so by the addition of fertilizers that help drive plant growth and thus yield. It might be good to begin with some definitions of legacy phosphorus. And the best that I can make it out, there's 2 working definitions, and these are not clear boundaries. They often bleed one into the other. So the one that I've gathered on the agronomy, on the soil science side, is that legacy phosphorus in soils is what is built up from past applications. Now, this is agnostic to the timescales. We could have had a large dose of phosphorus added as a fertilizer or as compost last year or 100 years ago, but it wasn't used by the crop in that time period, and so there's a net increase. So think of this as a positive balance of this stock of phosphorus in the soil profile. The other definition that you'll see that perhaps more of you are familiar with is what I think of as a water-based definition. And this is in the conceptual figure by Jarvie on the right-hand side, what's going on in the blue stuff. So this is in reference to once we have transferred the sediment into the water body or into the channel, that then can also be thought of and is talked about as legacy phosphorus. This can be confusing because if you talk to a soil scientist or a water scientist, you'll hear the same term being used, but they mean very different things. Note though that there's a causal link between these. Now, I think the key difference here is that legacy for soil science is more about balance. It's a positive balance that you've accrued phosphorus. And more implicit in the water quality term, and again, this is my take on it, is these lags, that there's a legacy, meaning that something that was loaded as sediment into the channel is still making its way down that channel. And that slow tumbling on the stream bed, for example, might occur at much larger timescales than the ag activities like erosion from tillage that first loaded it into the channel. So in other words, there was an erosional event that led to sediment loading into the river. It may take many more years than that one event for it to reach the final destination. We're going to focus on the first one, but already we can see a clear causal link for integrating the soil science with the hydrology. So that's two ways to think about it. Then you might ask, well, Andrew, why do we care about legacy phosphorus? And I think there's two ways, again, to think about this. One is environmental, one is agronomic. And I'm sure we've heard of the former, the latter, maybe not so much. So there's two of each type. Environmentally speaking, we would care about this because besides the fact that it can lead to water quality being compromised, that the lag times might lead to a decoupling of a practice that seeks to decrease P loading to surface waters from that translating to an outcome. So in other words, if there's planting of grass buffers or reduced tillage in a watershed, you may not see those practices manifest in decreased P loads for some time. The second reason that we care is really it is one step beyond that first one. And that's that a lot of our targets, for example, in Illinois, we have a nutrient loss reduction strategy. A lot of our targets that seek to decrease P loading to surface waters, they may not be accurate. And as we'll end today, you'll see an example from the Baltic Sea Basin where there's some serious implications for policy, and specifically about being patient with policies that seek to improve water quality. It might take some time. Agronomically, there's two reasons as well. One is about P use efficiency, and this might almost be thought of as biogeochemical. If we think about phosphorus, how odd it is that it's largely in North Africa and what is largely Morocco. It's mined from these sedimentary deposits, and we redistribute this mineral of apatite across the world's cropland. So we're expediting the kinetics of weathering in some sense, and we're also diluting it across the globe. Biogeochemically, that's quite interesting, I think. And one way to understand how we're making use of that finite reserve of rock phosphate is what's called P use efficiency. This is simply a metric of how much fertilizer do we add, what do we get back out in terms of P that went into the grain. The problem is that legacy P might confound calculations of PUE. So unlike end use efficiency, we have really poor metrics of PUE. The second agronomic reason is that a lot of the fertilizer recommendations are predicated upon a concept of subsoil P supply power. Basically, in our systems, how much can the parent material, the loess, contribute to deep-rooted crops' uptake of phosphorus? But you might imagine if you've built up phosphorus over time, you've effectively changed that soil supply P power. We won't go into these too much, but put it on your radar. There's also some practical issues in terms of management of ag fields. This might be why we all know phosphorus losses to surface waters are important. I'm sure you've seen this before, this depiction of non-points, meaning agricultural largely, and point sources like cities, their contributions of nitrogen and phosphorus to the Gulf zone. And in our state, we know that we are the #1 contributor of phosphorus among all of the Mississippi Basin states. We're #1. Now, within the state of Illinois, as you can see on the right-hand side, this is not homogeneous across the state. In general, the less recently glaciated and thus hillier south region experiences more of these phosphorus losses, or let's say contributions to the estimate of statewide P loads. So these are non-point P losses, and non-point P losses, largely from agricultural fields. These are largely from erosion. So only about roughly 1/4 of the non-points, so 10% of the total, are thought to be coming from dissolved or reactive phosphorus. That itself can come from past applications, meaning legacy P, or from in-season applications where there's dissolution of the fertilizer, it can be lost by tile drain. Minor amounts, more or rather larger in magnitude, would be the surface runoff of DRP. Now, the state strategy to decrease our contributions of nitrate N and total phosphorus have a target of total P of the equivalency of about 8,000 metric tons, 8,300 megagrams per year. So that's what we're trying to get to by 2025. Ambitious targets, and for now, for a few years, there's been a lot of efforts, including funding, to do research and education on practices for farmers to help achieve this. Okay, so let's talk about then, those are the losses. Let's talk about the phosphorus use efficiency, because this is getting at the paradox of phosphorus that you might sniff out in a lot of the discussions on P, especially in our state. What you're seeing here is an estimate of phosphorus use efficiency. This is done at the county level, as you can see, and it's done by difference. So how they do this, meaning the USDA, is that you find out how much grain is being sold in silos in each county. And then you know that 1 bushel of corn grain has X% of phosphorus, of wheat, of soybean. And then you take that as a ratio of the phosphorus fertilizer sold in that county. So the ideal way to get PUE is for every unit of phosphorus fertilizer, what was the export as grain harvested? This is the next best thing. There's obvious issues here, like you might sell fertilizer in a different county and use it in the next county over. But on the whole, it's number one, the best possible estimate, and it gives you a good broad sense. Now, what you can see here is that the northern states, especially in the Corn Belt right here, we have a fairly high PUE relative to other states in the union. And globally speaking, PUE is thought to be about 16% is the median value. So this is globally across cereal croplands. So if you look at the fact that that much of our state is above 80% PUE, done by this apparent high difference calculation, that looks pretty good. Now, there's issues with this, like the county approach. There's likely overestimation of this because of PUE, because crops can be using past phosphorus that was used, not that season's application. We might be overestimating because of the legacy P. But long story short, it's clear that in Illinois, we may have some of the highest loading of P to the Mississippi, but we also have some of the highest use efficiencies. So this then is what you might think of as a phosphorus paradox of how is it that we're overall efficient agronomically, but still are witnessing some pretty high, the highest of the union loadings to the Mississippi. Well, I think it's not really a paradox. Paradoxes don't exist. There's really poor explanations, or that's one way to think of it. And it's really just that there's a difference in magnitudes of what constitutes a lot for ag versus for water quality. Here's a way to think about it. What we have here is a map shown in very odd units for agriculture. This is in kilos of phosphorus per square kilometer. And as you go darker, you've got higher loading. And if we translate these into the scale of agriculture, it comes out to 200 kilos per square kilometer. So let's say the lower end of this dark color, this would be about 2 kilos of P per hectare. If we think about a typical application rate of 200 pounds of diammonium phosphate fertilizer per acre, did the math for you from freedom units into metric, it's roughly 45 kg per hectare. So the proportion of what is being lost in the hot spots is only about 4% in proportion to what is being put on. So I'm saying proportion because we don't know if what is being lost was the fertilizer, but to give you a sense of the magnitude, 4% isn't so bad. If you invert it and you estimate P use efficiency, this means that you may have 96% use efficiency, but still that 4% is enough to cause big issues for water quality. So I think this is simply a story of different magnitudes. 2 kilos per hectare for agriculture, not a big deal. For water quality, it is a big deal. So we can have high P use efficiency, agronomically speaking, and still have pretty devastating impacts on water quality. Now, we don't really know that well if the phosphorus from that same year of application is driving this. And as a matter of fact, our best estimates, meaning those of scientists, is that erosion is the main driver. Here's just one example, very qualitative of this. If you look at soil erosion maps, they pretty much track with the hotspots of P loss. And in Illinois, again, we estimate that roughly 3/4 of our P loading to surface waters is from sediment, it's erosional P loss. Again, these are coarse estimates. Now, this already, you might be thinking, matters for legacy P, because if you've built up and you've accumulated more phosphorus in the soil, then the same erosional load will engender a higher phosphorus load. Let's talk now about how do we get some numbers on the magnitudes of legacy P. How much phosphorus has been accumulated in Illinois at different scales, so from state to county to watershed, or even down to the field scale. Now, there's 3 approaches that I want to walk you through, and then I'll show you a 4th approach that we're taking. So the 3 approaches that we'll walk through now are soil test trends, and then agronomic balances at 2 scales, either state or county level. So by soil tests, if you don't know, soil tests are simply what we refer to things like melic or bray extraction. These are brief 5 or 10 minute extractions of soil, and you measure traditionally orthophosphate, now it's total P by ICP. But the point is that you extract a small amount of phosphorus in the soil, and this is thought to be available phosphorus for the crop. Not really, but that's the assumption. And it's a minor component of the total soil phosphorus pool. So remember that legacy P has interest in the total pool, not just the extractable. However, the soil test, because it's being used by farmers to inform how much fertilizer they add, it's ubiquitous, and it does correlate fairly well in a positive fashion with total phosphorus. So higher soil test P generally means more total P, generally. So if we look at trends over time, if these test values go up or down, it might be an indicator of, well, changes in total phosphorus, and that might be reflective of legacy phosphorus. The other approaches are agronomic balances, and this is simply outputs minus the inputs. And if we think about PUE, PUE is inverse to the positive balance. So let's let that sink in. Positive balance, we're accruing phosphorus, which means that we're not using it. So that would be antagonistic to P use efficiency, less efficiency of that application because it's not going into the crop. How we do this, conceptualized here, is you think of inputs as what you're adding, and the magnitudes that matter in general are going to be feed and fertilizer. And in our state, we're largely livestock poor state compared to other corn belt states. Fertilizer is the name of the game for Illinois, by and large. Outputs, again, then for our state would be largely crop harvest. The grain of corn, soybean, and wheat is what has a lot of phosphorus. And these might also be sources in livestock systems of outputs. These are unintentional outputs, but nonetheless, they're outputs. Now, the balance between outputs and inputs leads to the accumulation in the soil. Luckily, for us, there's no gas phase of phosphorus. So for studying its biogeochemical cycling, it's easy. It has to be in the soil, unlike nitrogen, which has a gas phase. The terms here are accumulation or depletion / mining if we have a negative balance. Let's look at what this looks like for Illinois. Well, let's start with the soil test trends. What we've seen is that in the last roughly 14 years, from 2001 to 2015, I know this is 6 years outdated, if we look at the US-wide trends and the trends in our state, we find that the soil tests of bray phosphorus, a common soil test for this region, that we have a similar distribution of the values. And I mean this in 2 ways. One is that between the 2 years, and then overall in terms of the magnitudes. So let's start with the magnitudes. If you're above this dotted line, above the value of 30 ppm, as a farmer, you wouldn't fertilize because the crops won't respond anymore to more phosphorus. So above this line is a waste of fertilizer. It also entails a DRP runoff risk. And the overall distribution is similar for the US as for Illinois. We have most of the soils are around the recommended value of 10 to 15, but then we've got some really high testing sites. Same too for our state. Now, through this time period, if we calculate the difference, so I took the difference between these 2 years, 14 years, we can now think of this as the drawdown. So from 2001, excuse me, to 2015, how did these test values change for the US and for Illinois? And what we find is that there's what's called drawdown. There's a decline in the proportion of soils testing at these very high values that pose financial and environmental losses for phosphorus. And there's an increase in the lower testing values that are coming at the expense of this. This is a good thing. We don't want to be above that red line for agronomic and environmental reasons. Now in Illinois, we've enhanced, or we have a, let's say, more amplified trend. We have a larger relative decrease in the highest testing values. That is a good thing, and a larger increase in the lower values that are agronomic optimums. So this is thought of as drawdown in agriculture. We're drawing down the unnecessarily high test value. If you think about legacy P, drawdown effectively entails a negative balance. And so this might be suggestive of, in the last decade and a half, roughly, there's been no legacy P made. There's just been a small mining amount. Now, this is super coarse, right? We're not getting at balances, we're getting at concentrations, the soil test P, and trends of those concentrations, and at the state. So let's look at balances now in more resolution. This is agronomic balances, so outputs minus the inputs at county level. Note that the years go well back beyond the data that you just saw. We're going back to 1987. What we can make out here is that if we think about the balances, either negative in orange and positive in blue, and these are magnitudes that are translated into kilos per hectare, we find that there is an increasing trend of how many counties and how strongly negative their P balances are. Things get more orange, deeper color of orange, so more of a negative balance, and there's more counties. Now, it does fluctuate year to year. This reflects that this is USDA data on P fertilizer sales and on grain harvest. So this is related to the PUE diagram that we saw. We've looked at a different source. This is a state database versus a federal database, and in a different year, to be fair. But the key here is that we still see largely negative balances in many counties. So this one county here has a pretty high positive balance, but there's a lot of small but persistent negative balances. This is clearly quite noisy, right? And it's also a balance. Remember that legacy P is the difference. If you integrate the area beneath the curve of these year-to-year balances, that would be what we're really chasing. So balances help us get to the legacy phosphorus. Let's look now at a balance that was published 21 years ago now, looking at phosphorus balances at the state scale. This was done by Dr. David and Lola Gentry, and this basically was looking at different sources of phosphorus. The key thing here that we're going to focus on is net inputs as inputs of fertilizer. We've got, for reference, sewage production, so a point source, manure, which is not really a net input. So because of that reason, we're going to cut it out. And then the export of phosphorus in rivers, these little triangles here. So note that overall, we have decreased the recycling of phosphorus at the state scale, less manure, more net inputs as fertilizer. I modified this graph by stripping out the net inputs. Oh, that was the wrong thing, folks. I'm sorry. So I've taken out the manure trend line to make this more simple. So now we just see here inputs in circle. We've got the sewage, which I like because it serves as a nice baseline. And we've got the riverine export creeping up here. So think of this then, if we look at what is above and below the zero line, we could think of this as a way to look at the accumulation of phosphorus, i.e. legacy P. Now, for some context, shown here is the more recent county-wide assessment that we've done with USDA and Illinois Department of Ag data. And we can see that the increasing negative balance is consistent with the negative balance beginning in the 1990s. And this might be persisting through the 2000s. So evidence that now in the last, maybe 25 to 30 years from present day, there's been a negative balance. But that's a current negative balance. Again, the legacy P is integrating the balance. And here's what I've done is that I have colored in the area beneath the curve showing accumulation. these would be net inputs, a positive balance. And it's this area that would represent legacy phosphorus in soils. We have some moments of net mining. As you can see, this was pre-World War II. There was limited use of phosphorus fertilizer. And we have more recently what I was mentioning, what we're witnessing, the negative balances. But if you add up the amount of how much phosphorus was added, the megagrams of P per year, it's quite a bit. There's a lot more green than red. So safe to say there is definitely a net positive balance, hence a large magnitude of legacy P. Now, how large is this legacy P? If we estimate this at 2 million megagrams total, how much is this relative to soil P stocks of the state? Some quick math, assuming we're looking at just cropland, and we make some assumptions about soil phosphorus stocks, the number is a big number. So we've got 48.5 million megagrams of phosphorus in the top 1 meter of soils under ag that would be receiving these inputs. And again, I mentioned how it's roughly 2 million megagrams of P is the area that's in green, roughly speaking. So this legacy P entails an enrichment of roughly 4% of what is native soil phosphorus in the top 100 centimeters. So again, very coarse balance, right? We're talking state scale, and these are more or less numbers. Okay, I'm mindful of the time here. Now, a few things here that we saw in the early slides, the conceptual diagram by Jarvie about lag times. You might see this as evidence of that lag time. We've been accruing a lot of phosphorus in green beginning by the 1960s, and a lot happened in only 25 years. And it was only in the very last part of that period of net accumulation that we saw an uptick in the riverine export of phosphorus. So this right here might be an example of legacy P in the soil science sense, and then in the water quality sense of a delay. And note that that export is still continuing to the rivers, even with the current negative balance. So this is why we need to account for the magnitude of legacy phosphorus and the mechanisms of its transfer from soil to water to better understand why, even though, for example, we're not fertilizing as much as what we're exporting with crop harvest, why then do we still see phosphorus loads in rivers being maintained, or as we saw a couple of weeks ago with the biannual NLRS report, why it's actually increasing. So here's a fourth approach that I'll end on is how we can quantify legacy P phosphorus. And the approach that we've begun is to do a pedological approach, meaning quantifying phosphorus at the scale of horizons in soils. A bit of background on how this is possible, and you'll note we're incredibly lucky that we have this resource. So we have on our campus an archive of soils that were done in the soil survey, began in 1899, plus some older collections from 1861 through present day. Now, most of these pedons are collected, as you can see, in the middle part of the 20th century. This is really quite important because being pedons, we have them sampled by their horizons, and they were part of the soil survey, either state or then federal. And as a result, we know where they were sampled. We had the original soil by horizon. We know where they were taken. So we can resample these to establish a chronosequence of total phosphorus stocks. This then is a direct application getting at the heart of what legacy P is, which can complement the triangulation, but it's now a direct measure. It's also at a scale that interests us, which is going from county down to the pedon scale. We skip over a few scales, spatially speaking, in the middle. But so to give you a sense of this, these are jars in the archive on campus. There's, we estimate, roughly 20,000 jars. So far, we've inventoried about 6,000 of those. And each jar has an identifier like this. This one right here is from the marl plots on campus from 1913. So the survey ones are like the marl plots. They're old soils. And again, they're done by the horizon. Because we have bulk density data, we can reanalyze these samples now for total P, no gas phase, it's still there. Resample the location of these pedons. Here's how many could be out there. And then construct this really nice chronosequence with high temporal and spatial resolution. So then that's what I want to really present to you. I leave you here with a couple of questions for the discussion now, which is understanding the how much and how fast of the transfer of soil legacy P to surface waters, to me, that would be the next step. So what our group is trying to work on is let's get some accurate numbers on the magnitudes. I hope I've shown you that the triangulation approach is a good qualitative estimate, but we'd like to have finer scale, numbers on legacy P. And also think about where it is in the speciation. So not just a total number, but where is it vertically speaking in the soil profile? What's the speciation? Is it as de novo calcium phosphates that are precipitated? Is it iron oxide based? Is it largely in the non-occluded pool? These are things that we don't really know too well. Once that's established, or perhaps in tandem, I think then the next step is to link this with the processes, both the magnitudes and the rates of transfer of the legacy into the streams and into the channels and then into the Mississippi. So this is where I'm fairly ignorant. I'm a soil scientist, and I see there being a clear need for soil scientists to work with hydrologists. I don't know if we've got time for this. So what I'll do is that I'll just give a very quick overview. Basically, here's a final reason why we should care about legacy P from the implications for policy. The Baltic Basin, shown here in the north of Europe, is a good example of why legacy P can really cause lag times that might appear to undermine practices to decrease P loading from agriculture. So long story short, the Baltic Sea Basin is like the Gulf of Mexico insofar as that it is receiving P from the surrounding basin, and it's largely from agriculture, but also from non-ag sources. And in terms of the contributions of P to the Baltic Sea Basin, we can see that legacy P that is able to be mobile, either as DRP or as erosion, it's a pretty good chunk of what's been added, and it's been increasing over the years, as we can see from this red part. All right, well then, what this study did in the Baltic Sea Basin was quantifying that in future scenarios, this major contribution of legacy P to the total P load would slowly decrease, even if you pretty much got rid of all P fertilizer application. So this is a good example of how the lag times, they can be, quite profound. And if we're talking about things like the NLRS, trying to encourage BMPs, best management practices by farmers, as a way to draw down on P loading, that can only move needles so much, depending on how much legacy P is driving those total P loads. So it makes sense to quantify legacy P soils and then soil to water transfers to, quote, get it right, to have accurate targets of what could be drawn down. Okay, so with that, I'm just going to skip to the thank you. Thanks for your time. And I'd be happy to have a discussion now with the group about what you see from your realm of geology and hydrology, soil science, how these can all be integrated on the legacy P topic. Thank you.
Thank you, Dr. Margenot, for a great talk and sharing your research idea. You guys are welcome to unmute yourself, and we are happy to hear your comments and questions.
Yeah, Andrew, I'll start out. Bruce Rhodes, hi. Great talk. I really enjoyed it. In my world, the term legacy is really used to refer to sediment rather than, of course, phosphorus. And it really refers to sediment that has accumulated in river systems through storage, and particularly storage related to human impact. So of course, if we look at something like a floodplain, just like you showed with the soil profile, we can have very, very old materials that predate any kind of agricultural activity on the landscape, particularly in the United States, where we have industrial agriculture being a relatively recent phenomenon. So if you, like, we're getting these cores out of the Sangamon River floodplain, and a lot of that material is going to predate any kind of agricultural activity. But then on the top, you have material that's accumulated on the floodplains or elsewhere in the river system from erosion. So that's how we refer to legacy sediment. Legacy sediment is sediment that's accumulated within the river system from human sort of induced accelerated agricultural erosion. And it can be identified. I know I see Dave Grimley's on the call or on the talk, and we've done some identification of this in the Sangamon Basin, but it's been done elsewhere throughout the Midwest. So this material is soil that's been eroded and then stored on the floodplains. So that's how we refer to legacy. And I guess what's interesting, I guess, in relation to what you're going over here is, first, I think that could be a potential storage area for a lot of legacy P, that if it's actually been accumulating in the soil, but then that soil is eroded and mobilized and moved to the floodplains and deposited there, that you could be accumulating legacy P on the floodplains in legacy sediment. And then that material gets remobilized by erosion in the river system, which keeps it, it takes it out of storage and puts it back into the river for transport. And I guess what's interesting is, the work that's been done on this for soil and sediment. There's been a lot of work in the Midwest, and what it's showing is that the time scale of this remobilization can be in the order of centuries, which would have incredible, sort of implications for phosphorus loading in streams. So sediment loading can remain very high, even if you control soil erosion, because you're remobilizing sediment that's stored through things like stream bank erosion. And I know you're working on this, and it may connect to things you're already looking at. But I think that might be one area that would be very fruitful for looking at interaction, is this relationship between the sediment redistribution process through storage, and then how that connects to the legacy phosphorus story.
Bruce,
so
thank you.
Very long-winded, but
No, that was wonderful, Bruce. Thank you very much for these thoughts. I have two questions or two thoughts. So one would be, I've read a lot about how streams, depending on their characteristics, can be a net sink or a net source at different timescales of. It sounds like this is what you're also describing, right? Of if you are in a floodplain, you could actually capture net phosphorus. Right. And then soils are pretty good at serving as a sink. It's hard to leach phosphates all the way through, but then they're vulnerable to erosion. So that's one thought, that soils are, it takes erosion to make them sources typically, but it seems like streams are more dynamic in the source to sink fluctuation, is my really coarse impression. Another thought that I have is, we're looking at, or in soil science, it's the quantification of the integration of the balance over a period of time that gets you the net total amount. So P stocks, how much more are they engorged from past applications? I wonder what that would look like for the sediments of channels. Is there a way to quantify the total? It'd be a huge number, the megagrams of sediment and the megagrams of phosphorus that are contained in the stocks, so to speak, of all the channels of the state, in the same way that we're quantifying in fields P stocks to 1 meter. Is there any work like that, Bruce, on trying?
I haven't seen any work like that. That would be, yeah. I mean, I think what would have to happen is you would have to be able to quantify the legacy accumulation of sediment in a very widespread way. And that hasn't been done. I mean, there's been some work in the driftless region, Dave's work I'll let him speak about that on the Sangamon, but we haven't done a widespread inventorying of legacy sediment that's being stored in floodplains. We're just starting to get, a handle on that, mainly because it's a difficult problem to address, and Dave's come up with some interesting ways to do it using things like fly ash. In the driftless region, it's quite easy because there's actually buried soil. You can see the buried pre-settlement soil very, very clearly and very visibly in the floodplain deposits if you either core them or they're exposed. But in Illinois, at least in the Wisconsin and glaciated area, it's a little less obvious what the post-settlement alluvium look is. So you have to first identify that, get a handle on its thickness, and then I guess you would need to, one thing we might think about, and I don't know anything about phosphorus, so excuse my naivete, but it might be interesting for you to look at some of these core samples and do some of the phosphorus analysis to see if you can detect potentially this wave of storage that occurred in the soil from your mass balance. Is that detectable in the actual stored sediment on the floodplain? In the post-settlement alluvium, can you actually see increases in phosphorus content in that upper part of the horizon?
Yeah, if I can jump in for a second. I think that crossed my mind too, Bruce, that maybe if he was interested, he could sample. There's the allergen cores, and there's also I still have all the original samples from the fly ash study that are more geographically dispersed throughout the drainage basin. I think I have 17 sites with, every 10 centimeters. So, if you were interested in that, we could discuss later, but I don't know how, I don't know much about phosphorus and if it degrades over time, or if it would give you the original signal from 80 years ago from a sediment that's buried, or would it still be? That was my question too, is how stable is it? Does it chemically react when it's sitting there?
Because if it's not stable,
then it wouldn't be possible.
I think it would. So first, David, thank you very much for that. That's pretty exciting. And I'll say I've been working with Andy and with Neil about the allergen cores, or communicating with them. I am salivating thinking about looking at total phosphorus to these depths. And the good thing I would say, David, is that P having no gas phase, it lets us measure total phosphorus with pretty high confidence. In some soils that are stored for a very long time, you can use zirconium to kind of account for a change in the bulk density. We're talking about these archive soils that we have, but fortunately, unlike carbon or nitrogen, the lack of a gas phase lets us have pretty high confidence that for the total value, what you measure after some time in storage is what it was at the time of sampling. The one caveat would be the speciation of phosphorus. So if you're trying to do, say, chemical fractionation to look at apatitic phosphorus or organic phosphorus, that would be more vulnerable, I think, to changes in storage time or just deposition time from the time that it was put down.
Yeah, the other thing I would like to mention is that we have, Dave has the samples of floodplain sediment. And then we did an analysis at the whole basin scale in the Sangamon of lateral migration rates of the streams. So from that, we would be able to actually probably determine remobilization rates of stored phosphorus, which would be pretty interesting. Yeah, right, yeah.
You've got me smiling, Bruce. That's really interesting. I'd love to talk with both of you more after this about how we might work on that. So to me, that would be a great way to link this more high resolution direct legacy P assessment that we're doing on pedons with in that region, in these places that you've sampled the sediments and you've got a good sense of what's going on. I think that's where the link is ripe to be made.
So Andrew, Hey, Andrew, I don't know if you can hear me.
Yep, just fine.
Hi, Tim
Timothy.
Philly. So one of the things that I was thinking about is that when you're moving from sort of a potentially like a well-drained upland area, where, or even if it's just moderately drained, where it's predominantly oxic, you're moving it to a floodplain where you get a much higher frequency of anoxic conditions, and then the reduction of that iron, and then a liberation of that phosphorus. You have you have this, you know, slow bleed over time out of the system. And so it's one of the things I was thinking about with the cores we have from Iowa, where we've got like 50 cores, and I've kind of been scanning with XRF, and you can see an iron nose at depth, because you've mobilized stuff from above and it's come down and it's changing its redox. How might that factor in? Because obviously there's a very close iron phosphorus coupling in that situation when you're looking at floodplain cores.
Yeah, I think that's a fantastic point. It's a thing that Shingan and I have talked about, is the speciation and also the reactivity. So yeah, iron and phosphorus, the redox in the stream channel. I'm not a hydrologist here, so, but in soils we know that Fe oxides, especially like goethite, the more amorphous short range order ones, are the driver in acidic pHs, or a very important driver, I'll say, of phosphorus. That's where I think looking at speciation would be quite interesting. So not just how much total P is in these sediments, but in what form is it? That might give some clues to the dynamics, the reductive dissolution, for example, that you're referring to with iron. I also wonder about calcium phosphates. Maybe they began as apatites and say the lust that was put down, but you can make short range order calcium phosphates under some conditions in soils at least. I don't know much about how that would occur, that chemistry in a saturated sample or in an aqueous sample. But this to me is important because a lot of the retention or the transfer of P from the sediment into the dissolved phase would be strongly influenced there. So that's another finer scale of the loading, not loading as in sediment P is in the channel, but also then it's being solubilized. That's a more tricky step. It seems like that would happen at much finer temporal scales, and it might be more complex because of the mineralogy of the sediment that was put down, things like this.
Yeah, I mean, there may even be a really interesting sort of feedback with the introduction of tile drains, which create that suboxic layer, which might retrap it.
Yes.
Mobilize and then trap again,
There are some very old publications by Furberbach, a pedologist that was here in the 1940s, where they did profile transects, and they looked at oxalate and dithionite extractable iron as measures of crystalline and non-subcrystalline iron, aluminium as well, and looked at P trends. And you often see where the BT horizon, the argillic horizons pop up. There's more clay, there's more iron oxides, and there's also a bulge in phosphorus. But then I couldn't agree. So that's what they were doing for some profiles across drainage sequences. And I'll try to dig this up. But long story short, yeah, when you're tile draining, I always wonder about the redox changes elicited by that. They have to have implications for phosphorus. Tile drain phosphorus losses seem pretty minor in magnitude. I've seen numbers of like 0.2 to 0.5 kilo of P as DRP by the tile per hectare per year, versus runoff can be a couple kilos of P per hectare per year from flat croplands. So it seems like it's a minor pathway, but
the introduction of that tile drain might actually induce a trap. I've got some really interesting cores that show that iron nose. That I don't know if you want to look at them. They're for one of our sites in the IML. Yeah.
Definitely. And then what interests me here too is legacy P. If it's Fe that's in a reduced state, you might think that there's more mobility in the profile. So maybe a lot of the past applications work their way down deeper. And I'm speculating here because there's less oxidized iron. And with tile drainage of these really wet soils, then yeah, maybe you not just stopped it, you also then locked it up in a form that's more recalcitrant. it's a shame that there's no second stable isotope of phosphorus for us to trace this.
Andrew, I just have another question about, not about the phosphorus actually, but about these legacy samples that you have in the jars. I don't know how accurately located those sites are around. It looked like, I was amazed how many sites you have on that map. But when you go back in the field, you were thinking of re-drilling some of those sites?
That's right, Dave. Yeah. So
one thing that occurred to me was, can you actually estimate how much erosion or accumulation there's been in those soils since they were sampled, or is that possible? Are they located accurate enough to do that?
I love the question, Dave. Yeah. So long story short, actually, first a caveat: these are the potential maximum of sites. This is based upon NRCS Surgo data. And so we have a collection that was not from the NRCS mapping effort. Illinois and California refused to work with the feds on soil mapping in the early 1900s. And so that's good because now we have in our campus this very early set of soils pre-1940. By the 1940s, it was more cooperative survey, NRCS, cooperative with the states. And so this is looking at just the federal database, what we could potentially have. These are all pedoms that were dug by a soil scientist to map soils. So I don't know if we have all these on campus, but we do have access to the federal archive in Lincoln in Nebraska. And obviously we could never, well, it would take a long time for us to resample all these pedoms across the state. But to answer your question, Dave, yeah, that's the thing that we've been thinking about is could you use some, the fallout from nuclear testing, for example, looking at the background radioactivity is what I understand as a coarse metric of erosional rates. If there's other ways of using elemental ratios to look at erosion rates, I think that would be quite interesting because there's a great paper by Jennifer Veenstra from Iowa State where they did a similar chronosequence approach for 50 years in Iowa. And they went from, I think, 1960 to 2010s. And they found that the mollisols were no longer mollisols because they had lost so much of their A horizon that they no longer made the taxonomic criteria of a mollic epipedon. So there's some morphological approaches that you could use from pedology to estimate the thickness up from an argillic horizon as a reference point to look at erosion. But I'd be very keen to discuss if there's more accurate ways.
Yeah, okay. Yeah, I was thinking more of just something simple, looking at the thickness of the A horizon, whether it's thickened or thinned. But I guess you're right. If there were geochemical changes in this that change those, that could it could be a physical and chemical aspects to it.
That'd be pretty neat. And then to link that with what Bruce is saying, with if there's sediment loading patterns, forgive me, Bruce, what you were saying about the sediments, I think what Dave is saying here, that would be a nice link in my mind of soil erosion and then where it went in the stream channels. That would be a pretty nice thing to link up in a watershed.
The other thing that we're going to be doing, which we should probably talk about, is we want to try to do this beryllium-7 sediment tracing of soil erosion on the fields and the delivery of that eroded soil to the streams, and also do sort of a mass balance of how much sediment's coming from the eroded soil on the slopes versus the stream banks. And we will be collecting samples of sediment that we could very easily build in a phosphorus component to that. So that we plan to start this fall. So if you're interested in that, let me know and we can discuss that.
I am interested. Yeah, thank you.
Yeah, okay.
Is that in the Upper Sangamon, Bruce, that you're doing this?
I think we're going to do that in the Kaskaskia, actually, because we want to be somewhere where we can get the samples quickly, because it's going to be event-based. It's all going to be kind of in relation to storm events.
Yeah.
So looking at how active runoff actually produces sediment, coming off the fields into the stream. Yeah. So you sample the beryllium-7 has a very short half-life, so we can only operate at kind of event scales to use it as a tracer. Yeah. But I can tell you more about that. But yeah, it'll probably be very close by, actually. So
I'm definitely interested. This is exactly
okay.
what I was hoping to share with the grouping to get out of it, is to think about how we all might integrate efforts on the
Right.
soil to water transfer.
Yeah, right.
Okay, thank you, everyone. I just want to point out that we are at the end of this seminar. And thank you, Dr. Margenot. It was a great presentation and discussion. We appreciate having you all.
Thanks for
And
having me.
the recording will be up in our YouTube channel, and we are gonna share the link later today. Hope you all enjoyed the session today. We will see you next time.
Thank you, Andrew.
Thanks, Andrew. Yeah, thanks.
Thank you, everyone, for
Very
having
good
me.
talk. Yeah.
Thank
Great
you.
discussion.
Mozgan, if you can stop recording and then you can transfer.